Hello everybody. In this video I will tell you about our work with Jinho bike on extreme values in real non-Hermitian random matrix ensembles. More precisely, we finally managed to compute the distribution function of the largest real eigenvalue in the real Ginebra ensemble. Now this had been an outstanding task for several decades, and while resolving it we actually completed three separate objectives. Number one, the identification of an integrable system for the distribution function of the largest real eigenvalue. Two, the derivation of tail expansions. And finally, three, the computation of a novel Fredholm determinant formula which is amenable to numerical simulations. I will show you now a few details of our work. First, the setup. So we're working with real Ginebra matrices, so just n by n square real matrices whose entries are IID copies of standard normal random variables. No symmetry imposed. This is in a sense, the most basic real non-Hermitian random matrix ensemble you can think of. It was introduced by Ginebra 55 years ago and soon afterwards popularized by Robert May in 1972. May in particular was interested in ecosystems, and he used real Ginebra matrices in his model. Here are some details about this. So he was analyzing multi-species predator-prey models that commonly you model here by a first-order autonomous ODE system with a fairly complicated, highly nonlinear right-hand side. Now you're interested in stability properties of that system because those will tell you whether certain species in your predator-prey model will eventually die out, right? So what you do is, of course, you Taylor expand the right-hand side, you linearize it around an equilibrium point of the system. You're working here, after all, with an autonomous system. That brings you to this level. So here bold X would be an interaction matrix between the different species, and mu just a scalar, say, self-regulating parameter. Now what May said is, how he argued is as follows. He said, well, in an honest predator-prey model, you're never going to know that interaction between the different species in all detail, so why not just replace it by a random matrix? And he exactly chose a real Ginebra matrix. Now at this point it should be clear why I'm interested in extreme values, because those extreme values, aka the spectral radius of the matrix X, will precisely tell you about the stability of solutions, aka the large time behavior of solutions. By the time of May's paper, 1972, not too many things had been known about the spectral radius of a real Ginebra matrix. What was known, this appeared in Genebra's paper in 1965, was the circular law. So in other words, the almost sure convergence of the underlying empirical spectral distribution. Okay. Now, if you look here at those pictures, you see a peculiar effect which is inherent only to real non-Hermitian random matrix ensembles, and that is what's going on here on the real axis. So on the real axis there's lots and lots of blue dots, those are eigenvalues. In fact, for an n by n real Ginebra matrix, for large n there are roughly square root n many real eigenvalues. This is known as the Saturn effect because, well, it just looks like a ring of a Saturn. Right? Saturn effect is a visually nice property, but it hints at serious technical difficulties when you're analyzing actually the fluctuations of the real eigenvalues around the boundary of the unit disk. And that's precisely what we did in our work with Jinho. Okay? About the fluctuations of the spectral radius before coming to the real ones, prior work by Brian Ryder and Chris Sinclair in 2014, so many years after 1965, settled the central limit theorem for the spectral radius coming from the non-real eigenvalues. Okay, of course, for large n, you're going to creep up to the radius of the disk, square root n, but you're going to fluctuate around in a rather elementary fashion, namely Gumbel distributed. What happened on the real axis was unknown till our work with Jinho in 2018, so roughly 2 years ago. What we did, we computed the central limit theorem for the largest real eigenvalue. Couldn't do the same thing for the smallest one. There's an obvious symmetry around the vertical axis. And what we did is we computed the distribution function of this limiting random variable chi here. Previous work also by Brian Ryder, Chris Sinclair, and Oleg Zaboransky, Roger Tribe, and Michael Pawlowski identified certain operator determinant formulas for the distribution function of chi. Our starting point were those formulas, and now we identified the integrable system behind them, so we dramatically simplified those formulas. Out came this very compact expression here. And this expression justifies the title of my talk, because Ginebra meets Schrödinger in this equation. On the left, we have, well, cumulative distribution function of random variable in Genebre's world. On the right, this special function P here, that sits in Schrödinger's nonlinear wave theory world. Okay, I'm not going to say much about the nature of P. P arises as a distinguished solution to a so-called inverse scattering problem for the Zakharov-Shabat system. Zakharov-Shabat system is an important object in the scattering theory of nonlinear evolution. PDEs, the 2x2 ODE system, has a fully fledged theory around it, but this is a little bit beyond the probability theme here of this symposium. Okay. For now, maybe just keep in mind the structure here. So exponent of antiderivative of this special function p to a square, and then another antiderivative of the special function. The structure is important because if you're familiar with the work of Craig Tracy and Harold Whittam on the Gaussian orthogonal ensemble, then you will realize that this formula is absolutely similar. The only difference to the Gaussian orthogonal ensemble, which is a Hermitian matrix model, is that function p is replaced by q, which is a Poincaré transcendent. Everything else is completely similar. Okay, now how do you arrive at such a formula? I will walk you through some of the details of the proof. So we proved this in much more general context, which is the context of thinned real Genebre processes. So you start with the real eigenvalues in the real Genebre ensemble. It is known for about 10 years that those form a Pfaffian point process. Now what you can do is you can thin out the process. Fix your parameter gamma and then throw out each particle independently with likelihood 1 minus gamma. That yields another point process. Now you compute statistical properties of that process. First one is, well, distribution function of the largest particle for finite n in the thin process. Turns out it's the square root of a certain regularized operator determinant. How can you prove this identity? Well, you prove a general result about a Pfaffian point process and when they are thinned out. Turns out a thinning procedure preserves the integrability, which is to say that the thin Pfaffian point process is still Pfaffian and there's a simple relation between the underlying correlation functions. Once you have this result, it's rather straightforward to get to this point up there. I'm not going to tell you many details about the underlying operator. Okay, now having this formula, now of course you want to push n to infinity, from the scaling limit, but there it's better if you first simplify everything. Here the simplification is carried out for even n's. This is a typical headache that persists in the analysis, very much like in beta equals 1 ensemble. In the Gaussian orthogonal ensemble, everything is parity dependent. Anyways, you simplify the previous formula on the other slide from regularized two determinant for matrix operators to just two ordinary phaton determinant of scalar operators. Scalar operator T is finite rank. Unfortunately, it's not a Christoffel-Darboux operator in the sense that this kernel is not a Christoffel-Darboux kernel coming from some orthogonal polynomials. And this is a serious issue. Okay? Now, once you have this though, you center and rescale everything correctly in order to obtain a meaningful limit, and the meaningful limit is written here in those two lines. Out front, ordinary phaton determinant of a trace plus operator T, T as the kernel as written down there, and then a determinant of a certain 3x3 matrix. That matrix depends on a bunch of unknowns, U, V, so on and so forth. All those unknowns are expressed in terms of the resolvent of this operator T. Here's one formula on top. Now, this is a perfectly manageable formula. However, it's really hard to identify an integrable system based on that formula, because there's the roadblock that T does not have Christoffel-Darboux structure. This is because, well, for finite n it didn't have it, and actually when n goes to infinity, the situation didn't get much better. The Christoffel-Darboux structure is very nice because once you have it, there's a machinery developed by Craig and Harold more than 25 years ago, which lets you identify the integrable system. So we had to bypass the roadblock, and this is actually fairly easy once you remember Fourier's world. So you go to Fourier space. This is our kernel. Each one here, the Gaussian one hump, you replace by Fourier integral. You have to integrate not over the real line, because otherwise the integrals are not convergent, right? You're going to replace each factor g here by one of those integrals, and then you want to commute the three integrals, so everything has to be nicely convergent, and this only is achieved if not all of those Fourier integrals are not on the real line. Anyways, once you do the computation, you realize that the product operator composition, more precisely, of T and chi-s multiplies by characteristic function of interval s to plus infinity. This composition is actually operator composition Fourier transform, some trace class operator E inverse Fourier transform. And this is nice because, of course, the operator determinant is invariant under the unitary conjugation of the Fourier transform. So actually the determinant on the previous slide is just the determinant of this identity minus E operator, and E turns out to have Christoffel-Darboux structure. Okay? With this little trick, you massage everything in Christoffel-Darboux structure, and now the machinery applies that allows you to extract the integrable system. At least for one of the two Fredholm determinants that I showed you earlier. The other one, the determinant of the 3x3 matrix, there you need a different tool set. Okay? After some calculations, out comes exact formula for the limiting distribution function, Tracy-Widom factor here out front, but not depending on Poisson-Levé function, but on solution to inverse scattering problem, and then some combinations of hyperbolic functions. Those functions are defined in terms of the antiderivative of solution to inverse scattering problem. So this is again where Professor Schrödinger appears. Okay? You can ask me whether this occurrence of a Schrödinger wave-type input is just an isolated curiosity of the real Genebri ensemble. Well, it is not. This was proven by Laszlo Erdős and his collaborators less than a year ago. They showed that the scaling behavior we discovered on the level of the largest real eigenvalue in the real Genebri ensemble is actually universal in a much bigger class of real non-Hermitian random matrices. In other words, this random variable chi here, or here in the thinned version chi gamma, defines a new universality class. That's why the work is even more interesting now. Okay, corollaries to it are the tail expansions. Tail expansions for gamma equals 1, so when you don't throw out any levels, had been computed by probabilists in Warwick, Zaboronsky, Tribe, and Fitzgerald using purely probabilistic arguments. Now here, having the exact formulas, having identified the integrable systems, we can prove those constant factors in a purely analytical fashion. Formulas are written down there. The last result I want to present is the simple Fredholm determinant formulas. While the integrable system connection is certainly nice, it is not so nice when you are interested in numerical simulations, because the solution to the inverse scattering problem is really hard to implement on the computer. Much easier are Fredholm determinants, simple Fredholm determinants, and here's a formula. It turns out that distribution function of the largest particle in the thinned Jinho E process is just a convex combination of two very simple Fredholm determinants. That operator S has a kernel which is as nice as it can possibly be. Okay, this is all I wanted to say. Thank you very much for tuning in. I want to thank Antti for organizing the session, and I will now finish by showing you the relevant references to our work with Jinho.